Alrighty, well, good afternoon and welcome to, what are we? We are Wednesday of week 6 for Chem 305. Today we will be polishing off our chapter 6. Sorry. Polishing off chapter 8, starting chapter 9. That is our goal today. I don't have any pieces of business, so let's just dive in. Excuse me. So we ended yesterday's lecture with a discussion of colligative, well, not a discussion, more like an introduction to colligative properties, and we basically said that category, colligative properties, simply means that adding solutes to a solvent changes the property, that the properties of the solution will be different than the properties of the pure solvent. And we said yesterday that whoa. Sorry, my marker is way chunkier than I'm accustomed to. There we go, dialing it back. I use my the Photoshop app as like an adult coloring book sometimes, and I was doing it last night, but I left my cursor super wide. So we said yesterday that adding solutes did several things. We said that first it lowers vapor pressure. We said that it increases boiling point, and it decreases melting point. All right, and that all three of these phenomena, the drop in vapor pressure, increase in boiling point, and drop in melting point or freezing point, was because, or should say, hang on, there we go, that these phenomenon are caused by the intermolecular attraction or intermolecular forces between the solute and the solvent. All right. So, for example, if you take boiling point, you've got, if you have a pure solvent, so we'll say just water, the only attraction in pure H2O is the attraction between water molecules, right? There is just H2O and H2O attraction here in a sample of pure water. If you compare this to a solution in which sodium chloride is dissolved, right? So let's add a solute. So now we have other particles. There's still H2 water attractive forces, but now we also have attractive forces between the solute and the solvent. So there's still the attraction between water and water, but we also have the attraction between water and sodium chloride. And so when you think about boiling, you're talking about having the water, the liquid, leave the liquid phase, go into the gas phase. You have to have enough energy to pull apart not only all the water-water attraction, but also the water-solute attraction that's going on. So it takes more energy, which is why the boiling point is higher. Okay, Susan, you bring up a really good point. So Susan said, I thought that for some reason I thought that salt added to water made it boil faster, so it's the opposite. And the answer is yes, but keep adding salt to the water that you're boiling. Here's the deal. It doesn't help it boil faster. It actually, like you said, it helps it boil, or makes it boil slower, because now you have to heat it up to a higher temperature. It doesn't make the water boil faster, but it makes your pasta cook faster. And here's why. When you add salt, the boiling point gets higher, right? That means the liquid water can rise to a higher temperature than it normally can, and with that water being hotter, it cooks your food faster. So it doesn't help it boil faster, but the higher temperature helps your food cook faster, and that is why you add salt to water when you're boiling, like pasta, for example. So, not a faster boil time, but a faster cook time is the reason that that technique gets used. And it's very effective, and we have colligative properties to thank for that. Totally cool. Totally cool. All right, so, and you can look back and you can analyze vapor pressure, melting point from this perspective. I'll let you read it in the textbook, just because we're a little bit behind, and I'm eager to move through the end of chapter 8 and crack into chapter 9 today. All right, so the last topic we have to cover in chapter 8 is that of osmosis. Totally. It's super cool to see real life applications of this stuff. All right, now osmosis is a word that we've all heard before. Mostly it gets kicked around with Hail Mary prayers, hoping that our lack of studying can somehow be compensated by absorbing the material in a way that doesn't require work. We're like, oh, I just hope I can absorb this by osmosis. But most of us don't actually know what osmosis is. Now, osmosis occurs when you have, two solutions with different concentrations that are separated by some sort of barrier. It's often called a membrane that can be crossed by the solvent. All right, so you've got a barrier between your two solutions of different concentration, and that barrier gets can be permeated by the solvent, but not the solute. Okay, when you have that scenario, osmosis occurs. So for example, if we have two solutions of water, all right, separated by a barrier, but we've got a membrane through which the solvent, or let's see, I don't want up there actually. So here the solvent can pass through. All right, it keeps the solute separated, but here the solvent molecules can pass through this barrier. And we have two different concentrations. Let's say we've got like 3 moles of solute on this side, and then this side will have way more. All right, just a ton, very concentrated on this side. What happens through the process of osmosis is the liquid, the solvent, flows from the less concentrated to the more concentrated side. All right, so solvent flows from the lower concentration to the higher concentration until they are equal. All right, that is the process of osmosis. So if they're connected through a barrier that solvent can pass through, the solvent is going to flow from the less concentrated side to the more concentrated side. All right, I'm putting these little markers in here to show that the solvent can pass until the concentrations of both sides are equal. All right, it's going to flow from the, like I said, less concentrated side to the more concentrated side. That is the process of osmosis. All right, so it balances. So the thing is, and this is the important thing to realize, is osmosis balances the concentration of particles, I should say, the concentration of solute particles. All right, that's what it does. It's there to ensure that the same number of particles are on both sides of the equation. All right. Now, it doesn't necessarily mean that the molarities will be the same, but the moles of particles will be the same. And you may be going, what do you mean, Josh? What do you mean? Well, consider this. Let's say you had a solution of 1.0 molar sodium chloride. All right. Now, we know that sodium chloride, according to our solubility rules, is totally soluble in water. What that means is sodium chloride doesn't, because it's soluble, it doesn't just hang out together in a group. It hangs out, it actually separates. The sodium cations float away from the chloride anions because that's what it means to be dissolved. So you'll notice if you have 1 mole of sodium chloride, that means in solution you have 1 mole of sodium cations and 1 mole of chloride anions. So together, your 1 mole of sodium plus your 1 mole of chloride means that you have a total of 2 moles of ions in that solution. All right. The number of ions that an ionic the number of particles that a compound in solution splits up to is called I. It's a lowercase I, and it's equal to the number of particles a solute, oops, not a solute, a solute forms in solution, all right, the number of particles a solute forms in solution is this little lowercase I, and we're going to use I to calculate a quantity known as the osmolarity. All right, this will be our last unit of the chapter, concentration unit. So osmolarity is equal to the molarity times I. All right. So, for example, if you had a solution of 0.10 moles of NaCl, the solution would have an osmolarity of, you multiply its molarity, 0.10 times 2. Because I, for sodium chloride breaks up into 2 ions in solution, so I equals 2. So 0.10 molar sodium chloride has an osmolarity of 0.2, say osmol. All right. If you were to do this calculation for, let's say we had 0.10 molar of calcium chloride. All right. Here, calcium chloride breaks up into 1 calcium cation plus 2 chloride anions. So since it breaks up into 3 particles, we can calculate its osmolarity by multiplying the molarity times 3. So we would say the solution is 0.30 osmolarity. All right. Now, the reason why we're learning this new concentration unit is because you can compare it, the osmolarity of one solution to the osmolarity of another, and predict which way the solution will flow. The solvent will flow based on the concentration, based on the osmolarity. All right, now the reason why this is important, the reason why osmolarity and osmosis is important, it's largely to do with our bloodstream. So you've heard that you shouldn't, that you can't drink ocean water, for example, right? Well, the reason why you should not drink salt water is because salt water ocean water, has a higher osmolarity than your blood cells. All right, and if you drink salt water, if you drink ocean water, because ocean water has a higher osmolarity, water will flow out of your blood cells into your bloodstream, all right, the solution around it, and it causes your blood cells to shrivel, like they shrink because they're losing the water inside them. They cause them to shrivel and collapse. All right. That is why we have the rhyme of the Ancient Mariner. I don't know if you've heard it, but it's the one that goes water, water everywhere, but not a drop to drink. Right? It's this guy whose ship has crashed, and he's on this plank. He's out in the middle of the ocean, surrounded by water, water, water everywhere, but not a drop to drink. If he drinks it, his blood cells will shrivel, collapse. He's going to die from drinking a aqueous solution. It's water, but it has a dangerously high osmolarity. Now, we have the rhyme of the Ancient Mariner, but what we don't have is the rhyme of the guy who started drinking distilled water because he didn't want metal in his water, right? I don't know if you've ever met one of these people who are like, there's metal dissolved in your tap water. There's metal dissolved in all these bottled waters. I only drink distilled water. Distilled water has no ions in it, nothing dissolved, zero solutes, all right? And you may think like, oh, that sounds like organic water. That sounds like the purest, healthiest thing I could do for myself. Well, yeah, Carenza, that is exactly why you've got to watch your sodium count, because if you have too much in your bloodstream, it'll shrivel and die. There's other reasons too, actually. It can affect heart function. So that's not the only health risk for having a high sodium diet, but definitely one of them. Totally. I'm glad I'm not the only one who. Yes, yeah, Carenza, that's totally true. Too much salt can and will kill you. Now, if you look at distilled water is dangerous for the same reason but opposite effect. Distilled water has a lower osmolarity than your blood cells. All right, it has a lower osmolarity than your blood cells. If you drink a ton of distilled water, now all of a sudden, so before with salt water, the salt water has a higher osmolarity, so water flows out of your blood cells. But now, since distilled water has a lower osmolarity, it has your blood cells have a higher concentration. So solvent starts flowing from your bloodstream into your blood cells. If you drink too much distilled water, it will cause your blood cells to bloat and burst. The opposite thing will happen, because all of a sudden you've got solvent, flowing from your bloodstream into your blood cells. They start bloating, and eventually they just start bursting. All right, so if you're thinking like, if you hear someone talking about how distilled water is the healthiest for you, it's actually not. The minerals in our tap water keep us healthy because they're at an osmolarity that's comparable to the osmolarity inside our blood cells, so it keeps them from shriveling or bursting. All right, those are the two. You want to stay away from the extremes. You want something right there in the middle. So the next time you hear someone say the government puts metal in our water, just know that they're doing that to keep us all alive. And actually they don't. Well, depends. Most of the minerals in our water, the government's not placing there. They're actually, it comes there from natural sources and where the water originates. Let's see. Oh my gosh, that's hilarious. There's a water sommelier. Well, I mean, you can get fancy schmancy, and putting different minerals in water will affect the flavor. Like the water that is on tap here tastes different than the tap water that I grew up with in Southern California, which tastes different than we would always go on vacation Montana, and our friends who lived up there who we'd stay with, they had well water, and it was their well was supplied by glacier melt, and that water tasted amazing and different. So we're not going to go into reverse osmosis, but it's basically you can alter the conditions to force water to go the other way, but it's not a thing that happens naturally. And reverse osmosis is used to filter out salts, to filter out solutes. So it's basically reverse osmosis is a purification method, similar to distillation, but it just uses pressure and filters. Essentially, Parthena, reverse osmosis is you force water through a filter that stops all the solutes, and then the water that moves out the other end is purified. Yes, Brianna, this is exactly where we're going. It's just to introduce a little bit of vocabulary to this mix. So we say that an isotonic solution is a solution that has the same osmolarity as blood. So we all want to be drinking isotonic solutions. Hypotonic solutions have a lower osmolarity than blood, and they cause cells to inflate and in severe enough cases burst. And then hypertonic solution, hypertonic solution is a solution with a higher osmolarity than blood, and this will cause cells to deflate and shrivel. All right, so those are the three kind of categories. Isotonic, same as blood. Hypotonic, lower osmolarity than blood, which causes inflation and bursting. Hypertonic, higher osmolarity, which causes the blood cells themselves to deflate and shrivel. Totally. And with that, we can put a pin in Chapter 8 and dive in directly to Chapter 9. All right, so in Chapter 9, we are going to discuss, dig into, look at different aspects of chemical reactions. Now, we already know what reactions are. Don't worry, Brianna, this chapter's not scary. We already know what chemical reactions are. We balance chemical equations. We know reactants, products, all that stuff. This is going to introduce really new types of chemical reactions. I'm going to hit on these first few rather quickly. We're not going to dig into them. I more just want to expose you to the vocabulary so you can kind of be familiar with what they are. So the first, let's see, 4 we're going to go through kind of quickly. But then we're going to park on redox reactions for a little bit of time. So let's get into it. So the first type of reaction, or actually, let me open a new slide. There we go. First type of reaction that I want to introduce you to is something called a combination. A combination reaction. And this is a reaction where you take two things, which I'm just going to call X and Y, and they react together to make a thing that I'm going to call Z. They combine to make Z. So an example of a combination reaction that we've already seen would be the reaction between nitrogen and hydrogen to form ammonia. Right, these two gases, H2 and N2, combine together to form a new molecule, NH3. All right, both nitrogen and hydrogen are in their elemental forms, but for combination reactions, you're not restricted to reactants in their elemental forms. For example, nitrogen dioxide reacts with hydrogen peroxide to produce two molecules of nitric acid. All right, and this is also a combination reaction. It's we're taking two molecules, we're combining NO2 and H2O2 together to make a new molecule. So they could be elements like nitrogen and hydrogen, they could be molecules, but a combination reaction is two things react together to make a new thing. All right, so that's combination, kind of the a very similar reaction, but just moving in the opposite direction would be decomposition. Right, a decomposition reaction. In a decomposition reaction, you start with something, X, and it falls apart. It breaks apart into two smaller pieces, which I'm just going to call Y and Z. So an example of a decomposition would be your friendly bottle of hydrogen peroxide that you have stored under your bathroom sink. Don't ask how I know it's there. I definitely don't break into your houses when you're unconscious and locate your bottles of hydrogen peroxide. That's just where we keep ours. Hydrogen peroxide actually decomposes into oxygen, gas, and H2O, liquid water. And this decomposition reaction is fairly slow, but it's the reason why, I don't know if you've ever opened like an old bottle of hydrogen peroxide, but when you twist the cap, it'll go like you're opening a soda can or something. That sound it makes, that real briefly, is the oxygen that's being produced that all of a sudden gets to escape when you open that cap. So it's literally pure O2 coming off of there. It's also a reason why, if you have an ancient bottle of hydrogen peroxide, you should probably just throw it away, because it's decomposing into oxygen gas, which will leave the second you open, and then what's all that's left is liquid water, and pouring liquid water on a wound to clean it isn't going to do much of anything. So throw away those super old bottles of hydrogen peroxide. It's just water at this point in time. So there's an example of a decomposition reaction. Decomposition reactions, the molecule doesn't have to break apart into two things. It could be multiple things. Like, for example, there's a reaction where you can heat nitric acid and it decomposes into nitrogen dioxide, water, and oxygen gas. So you can break apart into multiple things. It doesn't have to be just two. Decomposition is just start with one thing and then it breaks apart into multiple things, 2, 3, etc. Another type of reaction that we've brushed up against in lab actually is a displacement. All right, the displacement reaction, which looks like this. So in a displacement reaction, you have some compound X reacting with Y and Z, and it produces Y plus X and Z. The reason why this is called a displacement is because you'll notice that on the reactant side, X is by itself, and on the product side, it ends with Z. Whereas if you compare this to Y, Y starts with Z on the reactant side and ends alone. So the displacement reaction is the one in which X steals the romantic partner from Y, right? X ends up with Z and Y is left all alone. And this could be a happy or a sad thing depending upon the nature of Y and Z's relationship contrasted with X and Z's relationship. One such relationship that you have some experience with is the reaction between magnesium and hydrochloric acid. We spent a ton of time talking about this reaction yesterday. The products of this reaction are hydrogen gas and magnesium chloride. And if you look at it, magnesium starts this reaction alone but ends with chloride, whereas hydrogen starts as chloride's partner and ends as H2 gas. So there's the displacement, one for the other. We've talked about displacement reactions in another lab, but in the double, right? You can have a double displacement reaction, which we saw with the precipitation reactions. Yep, Kate, totally. We're switching the anion. Or in this displacement reaction, the cation switches. We trade one anion to the other. In a double displacement, it's the same thing, except it happens twice. It's A plus B gets together with X plus Y, and they both switch. So X ends with B, and A ends with Y. Double displacements are a little happier because everybody still ends up with somebody, right? You just have a swap of cation and anion pairs. A grabs Y, X grabs B, and those are the products you get. You saw these in the precipitation lab, right? So for example, aqueous silver nitrate reacts. The double displacement reaction, totally swingers. That is literally how that goes. The people show up with someone and show up to a party with a date and leave the party with someone else. So silver nitrate and sodium chloride react to make silver chloride, which is a solid precipitate, and sodium nitrate, which is still aqueous. But again, you can see that silver grabs chloride, sodium grabs nitrate, and that is how, that is how we get our products. All right. So that is the displacement and the double displacement reactions. We've seen some of these. Some of them are brand new. One very common equation that you'll see, that you have seen this semester, that you'll continue to see this, or I guess I should say this summer session. And you'll see if you have any chemistry in your future, you will continue to see this. And even if you don't have chemistry classes, you're still going to see, it's fun. And right, totally. Okay, good to know. Hopefully, we're all just thinking about swings at a park. All right. One reaction, though, even if you do not take any further chemistry classes, you will most likely still have experience with combustion reactions. All right. Combustion reactions are a staple of our everyday life, unless you're driving a Tesla. This is how our cars move around. And a combustion reaction is a very simple concept. You take something, some substance X, react it with oxygen, elemental oxygen, to produce an oxide. Right? You start with an element or a compound, react it with oxygen, and the product will always be an oxide. So, for example, one combustion reaction that we've used for a couple examples this semester is a reaction between H2 gas and O2 gas. The product here is water, H2O. And so this reaction, you can see that again, you start with some substance and you make an oxide. Now, we're not used to thinking of water as being an oxide, but if you were to name this thing, it would be dihydrogen monoxide, right? It's the hydrogen oxide product. Another combustion reaction, this is a lab that we actually do, or we do this reaction in a lab in Chem 400, is magnesium metal reacting with oxygen gas to produce magnesium oxide. Typically, when we think of combustion reactions, though, we're not thinking about metals or even hydrogen. It's usually hydrocarbons, right? So, for example, CH4 reacts with O2 to produce. Now, this one's interesting because you'll notice that we have carbon and hydrogen. And when a hydrocarbon is burned, is combusted with oxygen, you make two oxides. You make the carbon-based oxide and the hydrogen-based oxide. All right, so CH4 combusts with oxygen gas to make carbon dioxide and water. This is the reaction that you did if any of you cooked on a stove that used gas. CH4 is natural gas. This is what you use to make your eggs this morning. Also, if any of you have ever lit your flatulence on fire, this is also the combustion reaction you're doing. So we all may have experience with that combustion reaction in some context or another. All right, so that was a quick kind of like lightning round. 4 new reaction types: combination, decomposition, displacement, combustion. But this 5th type of reaction I want to park on for a little bit, because this will take a little more effort, and it's a very important reaction class known as redox reactions. All right, redox reactions. So, why are they called redox reactions? Well, redox is shorthand for actually, let's do this. Redox is shorthand. It stands for reduction and oxidation. All right, reduction and oxidation. And these processes. So reduction is a process, oxidation is a process. We've heard these words probably, but what they mean is reduction is a process where a compound loses electrons, And oxidation is a process where a substance gains. No, it's not. Okay, this is where dyslexia makes lecturing exciting. Reduction is a process where a substance gains electrons. And oxidation is a process where a substance loses electrons. All right, now how I know that and how I caught myself is with a little acronym. A little acronym that I use to help me remember is Leo says GER. Leo is an acronym that means lose electrons oxidation, and GER stands for gain electrons reduction. All right, this is not the only acronym. There are others out there like oil rig and whatnot. You can use whichever mnemonic helps you remember what it means, but this is the one that I rolled with because it includes my astrological sign. Not that I believe in astrology, but that's the one that stuck in my brain. All right, so reduction, electrons are gained. Oxidation, electrons are lost. Now, if you're looking at redox reactions in the light of these definitions, you may be thinking it sounds like a redox reaction is a reaction where electrons exchange hands. And if you're thinking that, you're absolutely correct. They in a redox reaction, one substance loses electrons. Oh, hey, there we go, dude. There's a lot of Leo love going on in the in the comments right now. Dude, oh man, Carolyn, you are 1 day off from my birthday. I am the 8th. So yeah, we'll be partying in about a month or so. What was I saying? Oh, right. So in a redox reaction, something is oxidized, it loses electrons, something else is reduced, it gains the electrons from that thing that's oxidized. So a redox reaction is a reaction where electrons are changing hands, right? So electrons are exchanged in a redox reaction. Let's take a look at an example of a redox reaction. All right, let's see this electron exchange in person. All right, the reaction of H2 and O2 to produce H2O. All right, do you see the electrons? You wait, you don't? I'm pretending I'm having a phone conversation, but you're only hearing half of it. You don't see the electrons? Here's the thing. That's because redox reactions are just like selling contraband, right? They're just like meeting up with your dealer. Everything's hidden. You don't actually see the electrons changing hands, all right? In every redox reaction, one compound shows up and is buying, the other one shows up and they're selling, but it just looks like everyone's normal. It just looks like people are eating chicken, all right? It just looks like you're chilling at Pollos Hermanos. Now, here's the thing. If a redox reaction is an illicit exchange, right, of electrons, if redox reactions are selling contraband, then you are the DEA, all right? It is your job to narc the situation. You have to figure out who's selling, who's buying by analyzing the chemical equation, and to do that, you need to know how to assign oxidation states. So this is going to be, these next few slides will be your years in the police academy. We'll come out the other end, analyze this reaction, figure out who's being reduced, who's being oxidized. All right? So I'm going to show you a 4-step method for assigning oxidation states. These are also called oxidation numbers. They're the exact same thing. One thing I want to point out is the method that I'm about to teach you is slightly different than the one presented in your book. If you look in your book will give you 7 rules for assigning oxidation states. I'm going to give you a different system that only has 4. All right, so it's about like half as many things to remember. Here's the thing: they both work. If you know the other way of doing it, you can totally roll with it. I don't force you to memorize this way. I just think this is a more concise method, and it's just simpler. It makes more sense. But anyways, if you read the book, you're like, this isn't what he taught us. It's because I taught you an alternate way, a different way of looking at it. But they both lead to the same answer. So roll with whatever is most comfortable for you. So the first rule when assigning oxidation states. So I guess first off, before we talk about assigning oxidation states, I should tell you what these are. Oxidation states oxidation states which I will abbreviate from here on out as just this. Oxidation states tell you the amount of charge an atom has in a compound. All right? They tell you the amount of charge an atom has in a compound, and this is where it becomes important for us, changes in oxidation state reflect electrons being gained or lost. All right, the whole reason why we're doing this is when you can assign oxidation states, you can look to see which elements have changing oxidation states, and those changes will reflect electrons being gained or lost. All right, so this is how you're going to narc out who is selling electrons, who's buying electrons. It's with this method. Now, these are the rules for assigning oxidation states. And you want to use these rules, you want to apply these rules as kind of a flow chart. Always do rule number 1 first. If that fails, move to number 2, then 3, then 4, in that order. They're ordered in terms of priority. So if you can solve it with just one, rule 1, stop there. If you can solve with 1 and 2, stop there, etc. All right. So rule number 1, and this is the most important one, the oxidation states of all atoms in a species must add to the total charge. All right, the oxidation states of all atoms in a species must add to the total charge. So, for example, if I asked you what is the oxidation state of sodium metal, all right, here for sodium, our total charge is 0, right? That means that the oxidation state of sodium is also 0. If I asked you what the total charge for aluminum 3 cations are, well, the total charge here is positive 3, so the oxidation state is positive 3. And likewise, if I asked you what is the oxidation state of H2, well, since the total charge is 0, that means the individual oxidation states for each hydrogen atom in this molecule must also be 0. All right? That is rule number 1. Rule number 2. Rule number 2. Hydrogen, so if rule number 1 fails you, you come back and you see if rule number 2 helps you solve the mystery. So hydrogen is always +1 unless it's the only nonmetal. Then it's -1. All right, so in a compound, hydrogen will always be +1 unless it's the only nonmetal, then it'll be -1. So for example, if I asked you to assign the oxidation states for H2O, hydrogen will have an oxidation state of +1, all right, because oxygen's not a nonmetal. That's rule number 2. Then rule number 1 tells us that the sum of all the oxidation states, so our 2 H's plus our oxidation state for oxygen, has to equal our total charge, which is 0. So that means +2 plus oxygen's oxidation state equals 0. So that means that oxygen has an oxidation state of -2. So H2O would be +1, -2. All right. What about in sodium hydride? Well, here in sodium hydride, hydrogen is the only nonmetal, so its oxidation state must be -1. That means for the oxidation states to add to 0, which is our total charge, sodium's oxidation state would be +1. All right, so here's a couple examples of using rule number 1 and rule number 2 to find the oxidation state of every element in a compound. Let's take a look at rule number 3. All right, so rule number 3, metals, metals in the first 2 columns on the periodic table have oxidation states equal to their normal ionic charge. All right, so if rule number 1 and rule number 2 aren't quite enough to get the job done, move to rule number 3. So, for example, let's assign the oxidation states for calcium chloride. All right, rule number 1 doesn't help us immediately. 2 doesn't apply because there's no hydrogens. Rule number 3 comes into play. Calcium's in that second column. Its normal ionic charge is a +2. And now that we know calcium, we can use rule number 1 to determine the oxidation state of chloride, because we know that the oxidation state of calcium plus 2 times the oxidation state of chlorine will equal our total charge, which is 0. Right? We subtract 2 from both sides of this equation, and we get 2 times the oxidation state of chloride is equal to -2. When we divide both sides by 2, we get that the oxidation state of chloride here is -1. All right? So so there's one example. Let's do another one. Just need a little more room. Let's assign the oxidation states for lithium, aluminum hydride. All right, now lithium aluminum hydride. Rule number 2 helps us out here. We have hydrogens, and hydrogen is the only non-metal, so it picks up an oxidation state of -1. Rule number 3 helps us out as well. Lithium's in that first column, so it picks up its regular ionic charge, a +1, and now we know enough to find the oxidation state for aluminum. We know enough because we know that the oxidation state of lithium plus the oxidation state of aluminum plus the oxidation state of our 4 hydrogens equals our total charge, which is 0. Lithium's oxidation state is +1. Hydrogen's oxidation state in this compound is -1. And this equals 0. So we're going to get aluminum -3 equals 0, which we now solve and find that aluminum's oxidation state is +3. All right, so there's using rules 1, 2, and 3 in tandem. Let's add our 4th and final. All right, rule number 4. All right, the last stop. All right, so if you don't have enough information based on rules 1, 2, and 3, then you move to 4, which states that the most electronegative atom will have an oxidation state equal to its normal ionic charge. All right, and we can now use all of these rules in tandem to solve, to assign oxidation states for compounds like the following. Yes. Oh. I'm so sorry. My intention is not to scare the study group. Let's assign oxidation states for sulfuric acid. And the only cure for terror in the study group and frontal cortex oxidation is practice. Just hitting a bunch of these. Can we just do the step first? So actually, so, and this is actually important. Um, so Karen's question. Oops. Karen's said, can we just step in and do rule number 4 first? Do we have to wade through the rest? And you can't. You must use it as a last resort only. And I'll show you why, not in this example, but in the one following. You'll see why you have to save it till the end. So first, going through these, we don't have enough information to apply rule 1. Rule number 2 helps us out. Hydrogen's always +1 when there are other nonmetals present. There totally are sulfur and oxygen, both nonmetals. But now, we don't have any metals, and we're stuck. We don't know. We have to use rule number 4. Now, oxygen is more electronegative, and so we're going to give oxygen its regular ionic charge of -2. And now we can apply rule number 1 to determine the oxidation state for sulfur, because we know that 2 times the oxidation state of hydrogen plus sulfur plus 4 times the oxidation states for oxygen will equal our total charge for this molecule, which is 0. Now we have 2 times +1 for hydrogen plus sulfur plus 4 times -2 for oxygen equals 0. All right, so we have a +2, oops, +2 plus sulfur -8 equals 0. So we have sulfur -6 is 0, which means that sulfur must have an oxidation state of +6. All right, this is using, well, not actually all 4. This uses rules 1, 2, and 4. We didn't actually need number 3 for this one. Carenza, let me do an example of if you apply rule 4 first, you'll get this one wrong. Let's do hydrogen peroxide. All right, first, we know that hydrogen will be a +1, and this is enough to solve, all right? This is enough to determine the oxidation state for O2. Sorry, not for O2, for oxygen. We know that 2 times the oxidation state of hydrogen plus 2 times the oxidation state of oxygen equals our total charge, which is 0. So we've written out this equation. We know the oxidation state for hydrogen is +1, and this gives us enough information to solve for the oxidation state of oxygen. So we have a +2 plus 2 times the oxidation state of oxygen equals 0. We subtract 2 from both sides of this equation, and we get 2 times oxygen equals -2. And then we divide both sides by 2. And we find that in hydrogen peroxide, oxygen has a oxidation state of -1. All right. So those are here's the deal. So this is where we're going to pause lecture. We now know, well, You've now seen the rules for how to assign oxidation states, all right? The thing to do now is to just practice this a ton. Practice it a ton. Get reps, assigning oxidation states, applying these rules. It's a lot all at once, but as you start doing it, it'll become more and more familiar. And here's the thing. The goal is not to determine what an oxidation state is. The goal is to use the information an oxidation state tells you to analyze a reaction to determine, is it a redox reaction? And to determine reducing agents and oxidizing agents. We'll be doing that tomorrow. For now, take a break. We've all been in lecture for, an hour and 20-ish minutes. Take a break, walk away, refresh, come back to it a little bit later. Practice this tonight, because we're going to be doing this tomorrow, but then applying this information. So let's get some reps in tonight, get more familiar with the process, then we'll start applying it tomorrow. And if we're still struggling with it tomorrow, we've got a glorious 3 hours of office hours together, right? So we have enough time to let this solidify. Cool? Okay. Thanks everybody for coming out. And I'll catch you all tomorrow. Later.